An inductive choker is a device that impedes the flow of alternating current, AC, by introducing inductance into the circuit. Inductance opposes changes in current flow, creating an inductive reactance that increases with frequency. When a conductor carrying AC current passes through a metal object, such as a locknut, it creates a magnetic field. This magnetic field induces eddy currents in the metal, which oppose the flow of current in the conductor. This opposition creates inductive reactance, effectively acting as a choke. In the case of isolated phase parallel conductors, the metal locknut can introduce undesirable inductive reactance into the circuit. This can lead to, firstly, increased voltage drop, secondly, reduced current carrying capacity, thirdly, power factor degradation, and fourthly, increased heat dissipation. To mitigate these effects, the following measures can be taken. Firstly, use non-metallic locknuts where possible. Secondly, use locknuts made of materials with low eddy current losses, such as brass or aluminum. Thirdly, ensure that the locknut is tightly installed to minimize any air gaps. And fourthly, consider utilizing a choke rated for the specific application to reduce inductive reactance. While the metal locknut can act as an inductive choke when used with isolated phase parallel conductors, it is important to mitigate its effects to ensure proper operation of the circuit. By implementing appropriate measures, the undesirable consequences of inductive reactance can be minimized. Electrical circuits operate on the fundamental principles of voltage, current, and resistance. Voltage is the electrical potential difference that drives the flow of current measured in volts. Current is the rate of flow of electrical charge, measured in amps. Resistance opposes the flow of current, measured in ohms. These three quantities are related by Ohm's law, which states that voltage equals current times resistance. In AC circuits, the presence of inductance and capacitance introduces additional complexities. Inductance is the property of a circuit element that opposes changes in current, while capacitance is the property of a circuit element that opposes changes in voltage. Inductance is created by the magnetic field generated by a current-carrying conductor. When the current changes, the magnetic field also changes, inducing a voltage that opposes the change in current. This opposition to change is what we call inductive reactance, and it is measured in ohms. The inductive reactance is proportional to the frequency of the AC current and the inductance of the circuit. Similarly, capacitance is created by the electric field between two conductors separated by an insulator. When the voltage changes, the electric field also changes, requiring current to flow to charge or discharge the capacitor. This opposition to change in voltage is what we call capacitive reactance, also measured in ohms. The capacitive reactance is inversely proportional to the frequency of the AC current and the capacitance of the circuit. The combined effect of resistance, inductive reactance, and capacitive reactance is called impedance, which is the total opposition to current flow in an AC circuit. Impedance is also measured in ohms and is a complex quantity that includes both the magnitude and a phase angle. The phase angle represents the difference in phase between the voltage and current waveforms. In a purely resistive circuit, the voltage and current are in phase. In a purely inductive circuit, the current lags the voltage by 90 degrees. In a purely capacitive circuit, the current leads the voltage by 90 degrees. The power factor is a measure of how effectively electrical power is being used in an AC circuit. It is defined as the cosine of the phase angle between the voltage and current. A power factor of 1 indicates that the voltage and current are in phase and all the power is being used effectively. A power factor of less than 1 indicates that the voltage and current are out of phase and some of the power is being wasted. Inductive loads, such as motors and transformers, tend to have lagging power factors, while capacitive loads, such as capacitors, tend to have leading power factors. Power factor correction is the process of improving the power factor of an AC circuit by adding capacitance or inductance to offset the effects of inductive or capacitive loads. This can improve the efficiency of the electrical system and reduce energy costs. Electrical codes and standards, such as the National Electrical Code (NEC), provide guidelines for the safe and effective installation and operation of electrical systems. These codes and standards cover a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. They are designed to protect people and property from electrical hazards. Article 300.3(b)(1) of the NEC addresses the installation of single conductors in parallel. It allows for the paralleling of conductors in specific situations provided certain conditions are met. These conditions include that the conductors must be the same length, same conductor material, same size and circular mill area, have the same insulation type, and be terminated in the same manner. The purpose of these requirements is to ensure that the parallel conductors share the current equally and prevent overloading of any individual conductor. Section 300.20(b) of the NEC addresses the issue of induced currents in metal enclosures. It requires that when conductors carrying alternating current are installed in metal enclosures, the enclosure must be designed to minimize inductive heating. This can be achieved by cutting slots in the enclosure or using non-metallic enclosures. The reason for this requirement is that alternating current flowing through a conductor creates a magnetic field around the conductor. This magnetic field can induce currents in the metal enclosure, which can cause the enclosure to heat up. In extreme cases, this heating can damage the insulation of the conductors or even cause a fire. The exception to 300.3(b)(1) addresses the use of isolated phase conductors in parallel. In this configuration, each phase of the circuit is run in a separate conduit. This is often done in high current applications to reduce the magnetic field around the conductors and minimize inductive heating. However, this configuration also requires careful attention to the insulation of the metal enclosures to ensure that induced currents are minimized. When isolated phase conductors are installed in separate conduits entering a metal-bottomed enclosure, a slot must be cut between the conduits as per 300.20(b). This slot interrupts the circular path of the induced currents, reducing the amount of heating in the enclosure. The metal locknut, used to secure the conduit to the enclosure, can act as an inductive choke. This is because the locknut is a metal object that surrounds the conductor. The alternating current flowing through the conductor creates a magnetic field that induces eddy currents in a locknut. These eddy currents oppose the flow of current in the conductor, creating an inductive reactance. The inductive reactance of the locknut can increase the voltage drop in the circuit, reduce the current carrying capacity of the conductors, and increase the heat dissipation. To mitigate these effects, non-metallic locknuts can be used. Non-metallic locknuts do not conduct electricity, so they cannot induce eddy currents. Locknuts made of materials with low eddy current losses, such as brass or aluminum, can also be used. These materials have lower electrical conductivity than steel, so they generate less heat. Ensuring that the locknut is tightly installed to minimize any air gaps is important. Air gaps increase the inductive reactance of the locknut. Finally, a choke rated for this specific application can be utilized to reduce inductive reactance. A choke is an inductor that is designed to block high-frequency currents. By placing a choke in this circuit, the high-frequency currents that cause inductive heating can be reduced. When dealing with electrical installations, specifically those involving parallel conductors and metal enclosures, understanding the principles of inductance and induced currents is crucial. The NEC provides specific guidelines in Article 300.20(b) to address these issues and ensure safety. Specifically, when conductors carrying alternating current are installed in metal enclosures, the enclosure must be designed to minimize inductive heating. The reason is that alternating current creates a magnetic field which induces currents in the metal enclosure, which in turn causes heating. The NEC requires either cutting slots in the enclosure or using non-metallic enclosures to mitigate this. The exception to 300.3(b)(1) allows for isolated phase conductors in parallel, where each phase is in a separate conduit, common in high current applications. In this scenario, when these conduits enter a metal-bottomed enclosure, a slot must be cut between them per 300.20(b) to disrupt the circular path of induced currents, preventing excessive heating. A seemingly minor component like a metal locknut can significantly impact the inductive properties of the installation. The metal locknut, being a metal object surrounding the conductor, acts as an inductive choke. It creates a magnetic field, inducing eddy currents in the locknut. These eddy currents oppose the current flow, resulting in inductive reactance. This inductive reactance contributes to increased voltage drop, reduced current carrying capacity, and increased heat dissipation. There are several mitigation strategies to address this. Firstly, non-metallic locknuts are an option as they do not conduct electricity and therefore cannot induce eddy currents. Secondly, locknuts made of materials with low eddy current losses like brass or aluminum are preferable to steel due to their lower electrical conductivity. Thirdly, ensuring a tight installation of the locknut is vital to minimize air gaps, as air gaps exacerbate inductive reactance. And fourthly, employing a choke specifically rated for the application can effectively reduce inductive reactance by blocking high-frequency currents that contribute to inductive heating. In conclusion, understanding the interplay between parallel conductors, metal enclosures, and seemingly small components like locknuts is crucial for safe and efficient electrical installations. Adhering to NEC guidelines and implementing appropriate mitigation strategies ensures that induced currents and inductive reactance are minimized, preventing potential problems such as overheating, voltage drops, and reduced current carrying capacity. Remember, a seemingly insignificant component like a locknut can have a considerable impact on the overall performance and safety of an electrical system. Therefore, it's essential to be mindful of these details and implement the necessary precautions to ensure a reliable and safe installation. When working with electrical systems, always consult the NEC and follow the manufacturer's instructions for all equipment. Safety should always be the top priority when working with electricity. It's essential to have a thorough understanding of electrical principles, safety practices, and the relevant codes and standards. If you are unsure about any aspect of an electrical installation, consult a qualified electrician. Remember that electricity can be dangerous, and improper installation or maintenance can lead to serious injury or death. So, always exercise caution and follow best practices to ensure your safety and the safety of others. The information provided is for general guidance only and should not be considered a substitute for professional advice. Electrical codes and standards are subject to change, so it's essential to stay up to date with the latest requirements. Always consult the NEC and other applicable codes and standards for specific guidance on electrical installations.